All right, this is Mr. McCord's AP Chemistry class. We've been looking at equilibrium, and more recently, how we mess up an equilibrium, how it fixes itself, how we shift the reaction around to the left or the right, more in the forward or the reverse direction, and how we kind of reestablish the relationship between the reactants and products if they affect the equilibrium. Okay, more recently than that, we've specifically honed in on precipitates, things that are insoluble in solution, so they are either in the solid form or they break up into their ions in solution. Okay, so what we did was called the common ion effect. We looked at how having an ion in common between two solutions together, added in, will affect the equilibrium. So, for instance, we took this calcium fluoride solution, right, represented over here, with black atoms for our calcium ions and white atoms for our fluoride ions, and we added in a solution of sodium fluoride, where green atoms are the sodium ions. Okay, so we toss those in. Bam, bam. Okay, and that increase in fluoride concentration means that this equilibrium is no longer the same. Okay, if this concentration is increased, our calcium concentration needs to decrease in order to rebalance that equilibrium. So our equilibrium needs to shift to the left, where we use up some of our fluoride to remake some of our calcium fluoride solid insoluble precipitate. Okay, so we would end up reprecipitating some of this stuff down here into the solid to make up for the fact that we now have more fluoride ions. And we called that, again, the common ion effect. Okay? That's just an extension of Le Chatelier's principle. And we can actually make another extension of the common ion effect, which is an extension of Le Chatelier's principle. So basically just another part of Le Chatelier's principle. This stuff is all going to lie in the same concept. Okay? It's just going to be a new way we apply it. So before, we were using a salt to kind of change the ion concentration of one of the things involved in that precipitate. Okay, the salt being something that is neutral, and it's an ionic compound that's not acidic or basic, and typically you can make it by putting together an acid and a base. Okay, this NaF would only break up into ions. It's a strong electrolyte. It just totally breaks up, and there's no equilibrium. Okay, but what if we dealt with something that is a little bit different? What if we use like a weak acid or a weak base? So let's try replacing something. I'm going to put these guys back. Okay. Okay. And maybe our sodium ion isn't a sodium ion. Instead, we're dealing with an H+. Okay, so this additional solution is not sodium fluoride anymore, it's hydrogen fluoride, aka this is going to be hydrofluoric acid in solution. HF is the molecular form of the acid in solution, and it can dissociate into H plus and F minus, but this is only a partial dissociation. A lot of it sticks around as HF. So this is another equilibrium. Now, what's the same is we are still adding a common ion, okay? The H plus itself does not directly affect how much CaF2 there is, but the F minus that comes along with it does. Now, measuring the fluoride ion concentration can be a little bit tricky. You know, you have to kind of come up with a great way to do it. And a lot of the practice problems that we do, we already kind of have it. It's like, oh, the concentration of this is this, the concentration of this is that. But in the real experimental world of chemistry, we have to get really crafty with how we obtain that information. Maybe we run an extra reaction to use up all of the ion to see how much of it was originally there, or maybe we have a colored solution that we can do spectrophotometry with. But in a case like this, we're going to have colorless solutions. So getting the concentration of a fluoride ion in solution is not very easy. Okay. Now, what we do have a lot of materials for is figuring out the pH of a solution, how acidic or basic it is. And this is a weak acid. It has a pH above 7. Okay? So, if my solution has been affected by this common ion that comes from a weak acid, now the common ion effect basically is affected by the pH. So, since the pH is just telling me basically, this acid basis basically, essentially how much H plus or OH minus is in my solution, okay, I can relate that back to however much of this is soluble. What is the solubility of this original compound? Okay, so the effect would still be the same if I put this into a solution of hydrogen fluoride. Maybe not to the same extent, but we should see the same kind of idea. If my green atoms are now representing my hydrogen ions, and just to recap for acids and bases, you might see these come up as H3O+. Same thing, we're just showing that water has taken that H+, and now it's together as the hydronium ion, but this is just easier to write and show. Okay, if I go throw this into solution, and again, this is a simplification. Okay, I now have some more fluoride floating around in my solution. So I will push the reaction back to the reverse direction over to the left. I will precipitate some more calcium fluoride so it is less soluble, just like we saw with the common ion effect. But now, these green guys here are H pluses. Okay, and however many of these are floating around free in my solution can be shown in the pH. Okay, however many of these guys there are tells me how acidic the solution is. Okay, so this is going to be way easier to measure, okay, compared to measuring the concentration of some other ion that's colorless in solution. In this example, we have magnesium hydroxide that is pretty insoluble. When it does dissolve, it breaks up, dissociates into Mg2+. Mg is being shown by black atoms, okay, and OH minuses. In the OH minus, the red atoms are representing oxygen, and the white atoms are representing hydrogen. Okay, so in a solution like this, okay, I would expect something like this, where I've got most of my MgOH2 still together as the precipitate, as the solid down here. Okay, but I do have some ions floating around in solution. I've got some Mg2+, and I've got some, should be together, OH minuses together. We're not going to have the O's and the H's completely split, because our hydroxides are polyatomic ions. That's my bad. Okay, so our solution should look something like this, and we can calculate the KSP, figure out the solubility and things like that by relating the concentrations of the Mg2+ to the OH minus concentration. So we got to mess this up. We got to change something up and see how it's going to affect the solubility of this MgOH2. So let's say that we add in sodium hydroxide. Right? Sodium hydroxide is a strong base. It's going to break up totally into its ions in solution. So we get aqueous Na plus ions. And aqueous OH minus ions. Hey, we've got a common ion. we've got hydroxide coming from both this equilibrium here and this strong dissociation here. So I'm going to represent my sodium with a green atom. And my hydroxide is still going to be red for oxygen and white for hydrogen. Like that. Okay? So, if I'm going to throw in some sodium hydroxide into the solution, or throw my magnesium hydroxide solution into the sodium hydroxide, then it might do something like this. Since this totally breaks up, I'm going to have just the Na plus ions, along with more hydroxide ions. Same thing here. Sodium ion, hydroxide ion. I have now increased the concentration of hydroxide in the solution. Which means, in order to fix the equilibrium that I've got between my solid and my ions here, I've got to use some of those OH minuses up. I've got to get less of this magnesium ion concentration. Okay? I've got to essentially use up some of my products to remake my reactants. This is going to shift the reaction to the left. Okay? Right? That might look something like this. Where I am using up some of my Mg2 plus and OH minus ions to remake some of the solid. Okay? Again, this is a vast simplification of how this might look. Redistribute those there a little bit. Okay? So, even though my sodium ion doesn't directly play into this, it's kind of the bringer of the hydroxide that does shift the equilibrium. Okay? Now, in this case, hydroxide is a basic component. So this is also tied into the pH of the solution. All right? If I continue to increase the pH, I climb higher and higher up the scale. So from 7 to 8 to 9 to 10 and on and on and on. My solution gets more basic, which means there should be more OH minus floating around in my solution. Well, the more OH minus there is, the more I've got to push the reaction back to the left, which means the less soluble this is, the more precipitate I'm making. Okay? So you could make a statement that the higher the pH is, the more basic the solution is, the less soluble magnesium hydroxide is. We could also take this the other way. Maybe I start adding in an acid, and I start neutralizing all of the OH minuses. So let's just throw it in there. Maybe we do HCl. So we have our HCl that we dissolve in solution. We get H plus ions and OH minus ions. Okay, so to represent my chlorine ions, what am I doing? Sorry, my chlorine ions, my chloride ions, let's do, I'm just going to use yellow. We said hydrogen is white, so we're going to keep that the same. Okay, so H plus, Cl minus are my ions that dissociate from my HCl here. Now, in this case, there are no common ions here. Mg2 plus and OH minus, are not in common with an H plus or Cl minus. Sure, there's an H here and there, but they're different species. They're different chemicals. So these ions are not the same. They don't play each other directly. But there is a reaction that can happen between them. There's a neutralization. Anytime I put together some acidic and basic solution, like something with H pluses and something with OH minuses, they're going to neutralize. So if I've got H pluses here, and OH minuses here, then those should react. Where the product is water. And we're going to keep this simple. Okay, so to keep this simple, we've got H plus ions and OH minus ions that are going to combine and neutralize into water. Okay, so let's say I go and add this stuff in. I take my HCl, dissociates, floats around in there. I take my HCl, dissociates, floats around in there. Okay, well, my H plus and my OH minus are going to form to make water. Okay, I can do it again here. Okay. Which has changed the pH. I have now put together some H pluses and some OH minuses. So the H pluses that I've introduced have kind of, in a sense, gotten rid of the OH minuses. They've consumed them in a reaction. So this has changed a little bit. Since our last equilibrium, we have actually decreased the concentration of OH minus by putting it together to make water. Find my purple marker. There we go. Okay. Which means we've got to make it back with that equilibrium. I've got to push my reaction now to the right to make up for the fact that I have now gotten rid of some of my OH minus. Instead of just physically taking it out, I had to use it up in a reaction, in an acid-base neutralization. Okay? So again, my chloride ions are not directly affecting this, they just kind of are along for the ride. But this is another tie to the equilibrium using pH. Okay? With a higher, more basic pH, we saw that our solubility decreased, so it should make sense that if we go the other way, we make the solution more acidic, we decrease the pH, we should get our reaction to shift back to the right, we should make it more soluble. Okay? So if your precipitate or insoluble compound of some kind is less soluble in basic conditions, it's going to be more soluble in acidic conditions, at least for what we see in this class. Okay, so we could continue to push this further and further and further, and continue to add more H plus and Cl minus, and those H pluses would continue to react with OH minuses, which would pull more of these guys out of the solid form and into our solution, okay, and more and more and more. So we would continue to make this more and more soluble, dissolve it more and more and more into those ions, okay? So our pH can work both ways, whether we are kind of playing directly with an ion that's in a precipitate or by taking it away by neutralizing it, okay? Now this isn't the only way that pH can play a part, because sometimes you have a compound that is not, being directly affected by a common ion, but the pH is still being changed. So let's look at a couple examples of those. Before we get too deep here, there is something we need to talk about that we've been kind of avoiding. And this is honestly usually best left for when we focus in specifically on acids and bases, like we would in Unit 8, but we kind of need to cover it now. So it's been brought up before that every once in a while we'll have a weak acid that breaks apart, and part of that comes out is a conjugate base. So if we had something like HF, it will break up into H+, which is kind of what makes the solution acidic, and that F- part is a conjugate base. So it makes the solution basic by going and finding a water molecule and taking one of the H's to remake HF, the molecular acid that is more favored, and leaving OH minus, which is basic. So the conjugate base isn't basic itself. It makes the solution basic by taking an H plus from a water molecule. Okay? And so far, that's been a good enough explanation to kind of settle it. And we now know that weak acids and weak bases are in an equilibrium, so we can better understand that most of the time they're stuck in the molecular form, and less often they are floating around as the ions. Okay, so in this solution of calcium fluoride, the F minus ions that we have, we can expect will go and pick up H pluses like this. Okay, but there's actually a little more to it. There's kind of a balance between water and the ions it can break up into, which sounds kind of wild. Usually we think of water as being this very stable thing, but in reality, we actually have a constant self-ionization where water will break up into an H plus and OH minus. Okay, now this is an equilibrium. All right, so we can write equilibrium constant expression for this. All right, so we use a K to show that it's an equilibrium. We're talking about water, so we're just going to use a little W. Kw for the equilibrium of water's self-ionization. Okay, so Kw is going to be equal to our products. In this case, H plus concentration times OH minus concentration divided by our liquid water. Well, we don't put pure liquids in there, so I guess that's just it. So Kw is equal to the concentration of H plus OH minus. Now, the basics of acids and bases, again, would tell us that H plus and OH minus should neutralize, which is true. They can come together and remake water in this equilibrium. But there are still going to be some H pluses and OH minuses that are left floating around. H2O will break up and release some H pluses and OH minuses in its own equilibrium. Okay? So this can start making the thinking part of these problems a lot worse, because then you're constantly doubting yourself. Do we ever really get rid of the H pluses, or do they react? Where are they? Are we ignoring it? Is that going to make my answer wrong? So let's just kind of back this up and keep it a little bit simple. Okay, this is a Kw. It's an equilibrium constant. It should have a value at 25 degrees Celsius. That value is going to be 1 times 10 to the negative 14th. Okay? Now, let's say that this is for a neutral solution of water. Neutral solution. A pure water. It's just liquid water. Okay? And we're not introducing any of these weird calcium fluoride stuff or anything else into this. Okay? Neutral typically means no acid, no base. Okay? But this equilibrium is saying there is still going to be some H plus and OH minus left there. Okay? Well, if it's neutral, maybe these don't combine to remake water, but we should have an equal concentration of H plus and OH minus. That's a better definition of a neutral solution. We have just as much H plus as OH minus. Okay? So, if H plus and OH minus are equal to each other, then we can kind of treat them as the same thing. So we could multiply those together. Okay? We could solve for the concentration of H plus or OH minus at any given time. Okay? In a neutral solution, you can find that H plus's concentration is equal to 1 times 10 to the negative 7th, and this is concentration, so it's going to be molar. Okay, well, you can also solve out for OH minus. Again, in a neutral solution, probably add that in there. In a neutral solution, OH minus should have the same concentration, so it should be one times 10 to the negative 7 molar as well. Okay, so what does this mean for us? Why are we bringing it up if it's just going to make things more complicated? Well, this helps us answer something. Why we can have H pluses or OH minuses to affect an equilibrium like the one we're about to talk about, okay? And why you might see some problems talk about a concentration of H plus in a solution that is certainly basic, okay? Typically we would think, okay, it's basic. That means OH minuses are there. That means no H pluses are there. But that's not technically true because this equilibrium is going to reestablish itself. So, in this equilibrium, if I have a basic solution, yeah, my OH minus concentration is going to go up. Shifts my reaction to the left to remake some water, which means I've got to use up some H pluses to do that. But there's still going to be some H pluses, okay? I've still got to have some concentration to plug in here and some concentration to plug in here to get this Kw value, to get the equilibrium constant. It is an equilibrium because I've got to have both of those present. The H plus and the OH minus have to be there in some concentration, okay? So in a basic solution, let me set this out. Our OH minus concentration is going to be greater than the H plus. It's not really correct to say that our concentration is going to be, only full of OH minuses and there's no H pluses in a basic solution. There actually are. And it's an important part of that equilibrium. In an acidic solution, we have a higher concentration of H pluses. Okay? Since we know what the usual concentration is when something is neutral for H plus and for OH minus, we can extrapolate that to a solution that is basic or acidic. So if I have a basic solution, then my concentration of OH minus is going to be higher than this. Okay, that means your exponent's going to be smaller, something like 10 to the negative 5th or 4th or 1st or something like that. Whereas my H plus concentration would go the opposite way. It would get to be a smaller number, which means a bigger negative exponent, like times 10 to the negative 10 or 11. Okay, we can flip it the other way. An acidic solution would have an H plus concentration that is greater. Okay, so it's going to start climbing up to the times 10 to the negative 5th or negative 4th, negative 3rd, and then our OH minus would get to be a smaller value, therefore a more negative exponent. Okay, so whenever you see something that shows H3O plus concentration or H plus concentration, or they're giving you OH minus concentration, be careful. That doesn't just mean that, oh, there's an OH minus concentration. That means it has to be basic, okay? It could be very much acidic because there's still got to be a little bit of OH minus left in order for this equilibrium to be there, okay? So be careful. Always check for that. It would be good to keep these numbers in mind, okay? Or at the very least, maybe keep this Kw memorized so that you can solve out for these concentrations when you have a neutral solution if you're kind of stuck on something. But if you can just kind of remember the 10 to the negative 7th, it's usually not too bad, okay? So at this point, is your problem solving going to absolutely rely on this stuff? No, but it could make or break a point here or there if you are not careful about looking at a concentration like this or this. If you kind of jump to conclusions, you can run into trouble. Okay, so with that little, not really little, really big sidebar, we should actually get to the problem of looking at how this equilibrium in water affects something like this, the solubility of a precipitate. Okay, I spruced up the right side a little bit to kind of organize it a little bit better. So our acidic or basic solution depends upon how the concentration of H plus and OH minus compare to each other. It's not just whether you have one or the other. Well, let's say we're trying to figure out how soluble calcium fluoride is in acidic solution. So we are going to kind of simplify an acidic solution as H pluses floating around and maybe a little bit of OH minus. But our concentration of H plus is higher than our OH minus concentration. Well, if these things were to go and associate with each other, okay, I've got H pluses that are positive ions. They're not going to go mess with this calcium 2 plus ion. They're going to go mess with this F minus. Okay, so if I've got an abundance of these positive H pluses, and they're going to do something about this equilibrium, they're going to go and do it with this. Okay, so my H pluses are going to start wandering around these F minuses and start to make HF. So we no longer have F minus floating around in the solution. We have kind of used them up in a separate reaction. Okay. In this case, my green stabs are representing fluoride, and my black ones are representing my calcium, and my red ones are still oxygen. Okay, so let's do this kind of magenta color. So I'm using these H pluses, H plus my, I'm just going to drop that there, my F minuses. That makes an equilibrium where HF is formed. Okay, so this means two things for us. For one thing, the formation of our HF means that we have used up and lost some of our F minus ions. Okay, so if we want to replenish those and reset the equilibrium, where are we going to get F minuses from? From our CaF2. We've got to break up more of that. Which means I'm going to have to push this reaction to the right. I've got to rush the forward reaction so I can get some more F minus ions floating around. Okay, so what does that mean in terms of solubility? Well, if I am making more ions with this, that means I'm dissolving more of my calcium fluoride. So my solubility is increasing in an acidic solution, where my H pluses extract my F minuses, and I wind up having to push the reaction more to make up for the fact that I've lost those F minuses. Okay? Well, how does that relate to the pH? My F minus is picking up H pluses. Those are, therefore conjugate bases. My F minus is a conjugate base, okay? And it makes the solution more basic, okay, as it picks up those H pluses. But it's still an acidic solution until I really, really, really push it far, okay? A conjugate base is not really as strong considering, compared to like an actual strong base or something. So if I'm in an acidic solution, I'm going to continue to drag away these F minuses, okay? And yeah, I'm going to use up some of the acidic protons in there, okay? But as a result, I'm going to push forward the equilibrium of calcium fluoride to the right to dissolve more of it. It's going to become more soluble. Okay, so you might be able to notice that this stuff runs away from itself very quickly. It can become very complicated. Okay, so stick to the facts. All right, our calcium fluoride is going to break up into its ions. If these ions are going to commingle with one of these or one of these, okay, and what we have most of, and what we're focusing on is our H plus in our acidic solution, it's going to go grab the F minuses. If we lose some of those, we got to make them back, which means we got to dissolve more calcium fluoride. So in this case, we ended up changing the equilibrium of calcium fluoride with an acidic solution, even though there was no common ion here. We didn't add in, specifically hydrogen fluoride. We just said it was acidic. It might have been HCl, or it could have been vinegar, acetic acid. It doesn't matter. All we knew that it was acidic. We had extra H pluses floating around. We had more H pluses floating around than a typical neutral solution. So we can figure out that that makes the calcium fluoride more soluble, pulling the reaction to the right towards the forward direction to make up for the fact that we're losing some F minuses as they go and bond with the H pluses floating around. Okay, so the common ion effect is not everything. Okay, sometimes pH affects something, okay, because of the presence of more H pluses or more OH minuses. Hydronium ions, H3O plus, again, are the same as these guys, just looks a little bit different. Okay, so pay attention to the pH. Think about what's in the solution. Okay, don't just think about it as like, oh, I feel like there's something I should know about the pH that I don't know. Write out what you have in there and work it out. How is your equilibrium going to shift? It's still a Chatelier's principle, even if there isn't a common ion in there from your acidic or basic solution. One last thing to kind of remind you of and to keep things fresh, okay? When we dissolve stuff, we've been looking at equilibrium constants, and we just recently brought back in acids and bases and all that. The way something happens in chemistry all comes down to two things: the change in enthalpy and the change in entropy, which those two things line up with Gibbs free energy, okay, like our delta G down here. Okay, so don't forget about thermodynamic favorability. Typically, when we look at how something happens in chemistry, if it's not driven by the kinetics, kind of the rate of the reaction, it's going to be drawn by the thermodynamics, which is what we've kind of looked at more so far. Okay, we've looked at how thermodynamics can kind of push something to happen, okay, in a favorable way. Kinetics, we just kind of looked at how the kinetics of a reaction have kind of occurred. Okay, so when we look at stuff dissolving or undissolving back into an insoluble precipitate, that involves pretty much three things that are happening here. And this is probably something we've touched on a little bit with the labs. So let's say I've got this calcium fluoride here that's a solid, and I'm throwing it into water. I've got my ionic bonds attracted between my positive calcium ions and my negative fluoride ions. So my ionic bond is a strong attraction I've got to fight against. My water molecules, right, are not bonded to each other, okay, but they are attracted with intermolecular forces. This is a dipole-dipole attraction because each water molecule has a dipole. It's got a polar end, right? One end is partially negative, like our oxygen here, and one end is partially positive, like by each of these hydrogens. And those have an attraction to each other, a partial attraction. Okay, so if I want to get these two to intermingle, I've got two attractions to fight. One of them is the ionic bond here, and one of them is the intermolecular force between water molecules. Okay, now you could be using a different solvent that has different attractions, but water is by far the most common solvent we use in chemistry at this level, and it's what AP is probably going to focus on, so we're going to stick to that. Okay, so end goal, to get this to dissolve, I need this to be no longer in an ionic compound. I need the ions to be separated, okay? And I also need them to be surrounded, and therefore dissolved, okay, by the water molecules. So, first thing I've got to fight, okay? And this is not really necessarily in order of events. This is just, let me say A. Step A, Well, that's also in alphabetical order. One of the things that needs to happen, I have to break this ionic bond. Okay? It could be to break off one of these fluoride ions, or maybe another one, or it could be to break out calcium ion, but I've got to break that attraction there. Okay? Ionic bonds are typically held together very strongly. Okay? So most of the time, that is going to take energy. That is going to be endothermic. Okay? Now, our delta H, all right, is a thermodynamic driving factor when it is exothermic, when it is a negative value, when we are releasing heat. This is going to take some heat. This is going to take some energy to break those bonds. So, not really favoring the process, okay? Especially for a precipitate. That means the ionic bonds are very, very strong, okay? Now, another thing I need to do, I need to break the attraction here, the intermolecular forces between these molecules, okay? Not as strong as a bond, kind of bond to attraction comparison, but it's still an attraction nonetheless. So I got to put in a little bit of energy to get those kind of separated too. Again, not really thermodynamically favored in that sense. Okay, so I'm going to separate one of these guys. Okay, now if I think about it, by breaking up this ionic compound, that also affected the entropy. Okay? Entropy is typically simplified as randomness or disorder, but really it's about how many microstates, configurations, options we have for our particles to be moving around. Okay? Now that this is no longer clumped into an ionic bonded compound, this has way more freedom of movement, which means my entropy has gone up. That is a driving factor. So that's good. My water molecule also is a little less ordered. Okay? So entropy is a driving factor behind that. Okay? So now these are a little more free moving. We had to put in a little bit of energy to get there, but now we've got entropy kind of winning out. Okay? What tells us whether this is kind of giving us a endergonic or exergonic reaction. Exergonic is kind of the fancy word for we are overall releasing free energy. We get a negative delta G value. An endergonic would be like a positive delta G value. We've got to, overall kind of make the situation less favorable. It's going to come down to how these kind of shake out, the delta H and the delta S. Okay? One final thing that has to happen is the attraction between these two things. If this ion is positive, I'm going to want to line it up with somewhere around the negative side of my water molecule. And if my fluoride ions are negative, I'll want to kind of line it up against the positive sides of this water molecule here. So we have new intermolecular forces. Now this is between ions and a dipole, so we call this an ion-dipole intermolecular force. Okay, so this is an attraction. It's putting things close together where they would like to be. So this part is going to be exothermic. We're going to release some heat as our potential energy changes here. So check off for that. Okay, so out of our three things we've done, we had to put energy in to separate our water, put energy in to separate our ions from each other from the compound. Okay, and then we favorably put them next to each other in a place they can attract. Okay, we got them to be more disordered and more disordered. Okay, but then arranging them next to each other also takes some order. On a large scale, okay, you're going to have way more water molecules that will surround these ions. Okay, so you're going to end up with more and more attractions there and more order there. Okay, whether this comes out to be a favorable situation, whether our delta G, our Gibbs free energy of our dissolution, our dissolving process, ends up being negative or positive, shows that the net process of all of this stuff is going to either be negative or positive, okay? By having enough heat released or enough freedom of movement, enough configurations created from this process, okay, overall. All right? So you may need to dig into how an ionic compound breaks up and then the ions kind of float around, how the water will separate and break up, and how they come back together to figure out either the delta G of the process or maybe the enthalpy change or entropy change happening individually kind of before that all kind of net process happens. Okay? So just remember, this is stuff that we have seen before. Okay? It's just a matter of putting it into a new perspective. Okay? A new lens to look through.